In the last video, we talked about using the increasing and decreasing test to figure out where a function is increasing and decreasing. And we realized that by doing that, it gives you a general shape of the graph, and it tells you exactly where your function is going to have local max and mins. And so the first derivative test is just formalizing that idea. It says if c is a critical point for a continuous function f, and if the derivative, f prime, changes from positive to negative at that value c, well, then that means that your original function f is changing from increasing to decreasing, right? Increasing to decreasing, not necessarily at a point like that. So if f prime is changing from positive to negative, then f changes from increasing to decreasing, which is exactly why f has a local max at c. Similarly, if the derivative function f prime is changing from negative to positive, then that means that your original function f is changing from decreasing to increasing. And that's why your function f is going to have a local minimum at c. The first derivative test also tells us that if f prime doesn't change signs at c, then it's not going to have a local max or min. So let's use a graph, or let's use a first derivative test to analyze a function f given the graph of f prime. So what we have here is the graph of the derivative of a function f. We're going to use that to find the local max and mins of our original function f, even though we don't know what f looks like. Now, based on the shape of this graph, this suggests to us that f prime is probably, right, this is a parabola, so f prime is probably a quadratic or an x squared function, which means x cubed, or which means that the sort of antiderivative, we haven't talked about that yet, but f itself is probably a cubic function, an x cubed function, if its derivative is an x squared function. So we maybe have an idea already of what the shape of that graph would look like. But using the first derivative test, we can figure out exactly where the local maxes and mins of f would be. So here's what we know of f prime. F prime is negative, right? It's below the x-axis from negative infinity all the way up to negative 2. So on this whole interval here, the graph lies below the x-axis. So f prime of x is negative, it's less than 0, on the interval from negative infinity to negative 2. The derivative is also negative, it's also below the x-axis from 3 on. So f prime of x is less than 0 on the interval from 3 to infinity as well. The only time this graph is positive or above the x-axis is in the middle portion here between negative 2 and positive 3. Here, the derivative is above the x-axis, it's positive. Okay, so we can sort of build this real number line like we were using in the increasing and decreasing test to figure out where the local maxes and mins are. The critical points are going to be at negative 2 and at 3, because that's where you're changing from the derivative being negative to the derivative being positive. Okay, so here we said that the derivative is negative on this interval. We said that the derivative was positive on the middle interval, it's above the x-axis, and the derivative is negative again on the last interval. So that tells us that our original function f is going to be decreasing on the first interval, increasing on the second interval, decreasing on the third. Okay, so we can see based on the general shape of the graph that we've sketched here that we have a local min at x equals negative 2, and we have a local max at x equals 3. So that's kind of a neat trick if you know the derivative to help tell you information about the original function f. Now, we're going to put these two things together now, the increasing decreasing test and the first derivative test, to talk about two more examples, two more functions. So let's find the increasing and decreasing intervals and find the local max and min for the following cubic function, 1/3 x cubed minus 2x plus 1. So we start off by following the same steps that we had followed in the last video for the increasing and decreasing step, or increasing decreasing test. Step 1 was to find any critical points of f. those are going to be points in the domain of f where f prime is either undefined or 0. And just like last time, this is a polynomial, so f prime of x is defined everywhere, and f of x is defined everywhere as well. So we want to know, where is f prime of x equal to 0? So take the derivative first. F prime of x is going to be the derivative of 1/3 x cubed is 1/3 times 3, which gives you just 1, x to the second power, minus the derivative of 2x is just 2. The derivative of 1 is 0. Okay, so we set this equal to 0 and solve. So we get x squared is equal to 2, and if we take the square root of each side, we get that x is going to be equal to positive or negative square root of 2. We have two solutions here, two critical points. These are our two critical points. The positive square root of 2 and the negative square root of 2. Now that we have our critical points, we move on to step 2, which is to break up the real number line into intervals using the critical points. Okay, so our critical points are negative square root of 2 and positive square root of 2. Okay, and we've already done that, so our intervals here would be negative infinity to negative square root of 2, then negative square root of 2 to positive square root of 2, and then positive square root of 2 to infinity. So we have 3 intervals, and we can move on to step 3, which is to actually test a point in each interval and determine whether the derivative function f prime, whether f prime of x is positive or negative on that interval. So plug in a point from each interval into the derivative function. Let's go back. Our derivative function is this function right here. We're going to test points in each interval to see if that derivative is positive or negative. Okay, so I need to choose a point for each interval. My first interval is from negative infinity to negative square root of 2. I maybe don't know right off the top of my head just exactly how big negative square root of 2 is, so make sure that you choose a point that's actually in this interval. Choose a point that's sufficiently large and negative. Like for example, you could plug in f prime of negative 2, and you should be hopefully convinced that negative 2 is going to be to the left of negative square root of 2. If I plugged in negative 2 into this function, I'd get negative 2 squared minus 2. This is 4 minus 2, so this is going to be positive. Okay, then I test a point in my second interval. If I test something between negative 2 or negative square root of 2 and positive square root of 2, I'd want to test something like 0. I get 0 squared minus 2. This, of course, is negative. And back to my last interval, plug in something bigger than square root of 2, like let's say just 2, and we'll get 2 squared minus 2, which is positive. Okay. Using this information in the increasing-decreasing test, I know that the original function f, right, this was all about f prime, but now I know that the original function f is going to be increasing on the first interval, then decreasing on the second interval, and then increasing on the third interval. So roughly the shape of the graph looks like this, right? Something like this, based on that increasing-decreasing test. Now based on the first derivative test, because the function switching from increasing to decreasing, the derivative switches from positive to negative here, I know that negative square root of 2 is going to give you a local maximum of the graph. So we have local max at 2 comma f of square root of 2. Now remember, maxes and mins are really outputs of functions, so I should probably plug that back into my original function, but it's fine to just say f of the square root of 2. Similarly, because your function changes from decreasing to increasing, or the derivative changes from negative to positive at square root of 2, that means we have a local min at square root of 2 f of square root of 2. Oh, did I mess this up? This should have been negative square root of 2 for the local maximum. positive square root of 2 for the local minimum. Right, this is our max, it's a peak, and this is our min, it's a valley. Okay, and similarly, we can be more specific and say exactly where this function is increasing. F is increasing on the interval negative infinity to negative square root of 2, union square root of 2 to infinity. In other words, the first and the last intervals. And F is decreasing on the middle interval from negative square root of 2 to positive square root of 2. Okay, so we used both the increasing decreasing test here and the first derivative test to conclude these things. Now we'll do one more example. And we'll analyze the critical points, of the function f of x is equal to the cube root of x minus 2. This is the first one that we've done where the function isn't a polynomial function anymore. Right, we have this radical function, the cube root of x minus 2. So just as a little bit of scrap work, I'm going to rewrite this as x minus 2 to the 1/3 power, because I know it'll be easier to find the derivative of this if I rewrite that radical as an exponent. Right, that's going to be just using the chain rule. So we go through our steps again. Analyze our critical points just means determine whether they're maxes or mins. So let's first find the critical points. This is step 1. Find the critical points of f. And this is where we want to be a little bit careful. Our function f of x is defined everywhere, right? We don't have to worry about negatives underneath the radical sign because it's a cubed root, it's an odd root, and odd roots are defined everywhere. So f is defined everywhere. F's domain is all real numbers, but possibly not for f prime of x. So we need to find where f prime of x is either equal to 0 or undefined. Those will be our critical points. So f prime of x we can find using the chain rule. We have a function being raised to a power rather than just x. So the chain rule says if this is sort of our inner function, our u, we take the derivative with respect to u, so bring down the exponent 1/3 times our original u function, x minus 2, raised to the power of 1/3 minus 1. 1/3 minus 1 would be negative 2/3. And then we multiply that by the derivative of u, the derivative of the inner function. Lucky for us, the derivative of x minus 2 is just plain 1. So chain rule doesn't give us anything too bad in this case. But I'm still going to try to rewrite this so that I'll have an easier time of figuring out where this is equal to 0 or undefined. I have the fraction 1/3 out front as a coefficient, then x minus 2 is being raised to the negative 2/3 power. I want to get rid of that negative exponent here. So I'm going to rewrite this and move this whole thing down into the denominator with the 3 so I can change my exponent from negative to positive. So I'll rewrite this as 1/3, that's where the 3 came from, and now x minus 2 is going to be raised to the positive 2/3 power. And if you wanted to really understand what that means, you could rewrite this one more time as take out this exponent of 1/3 and write it as a cube root of x minus 2 to the 2 power. Right? We don't always have to rewrite derivatives, but in a case like this where you're finding critical points, this is where it makes sense to rewrite the derivatives in a form that makes more sense to us computationally, right, than something like this. Now we want to find where this function, this derivative function, is either equal to 0 or undefined. Those will be the critical points. First of all, this function is never equal to 0. The only time a fraction is equal to 0 is when the numerator is equal to 0, but our numerator is 1, it's constant. So f prime of x never equals 0 because the numerator is constantly 1. But the denominator might sometimes be undefined, which means the denominator could be equal to 0, which would make this entire derivative function undefined at some point. So where is the denominator equal to 0? Well, anytime you get a 0 here, right? Whenever x minus 2 is equal to 0, then x minus 2 squared will be 0, and the cube root of that will be 0, and so the whole denominator will be 0. And so when x is equal to 2, right, when x is equal to 2, f prime of x would be 1 over 0, which is undefined. And so x equals 2 is our only critical point. Great. Okay, now remember what our next step would be. We're going to break up the real number line based on our critical points. Put -2 here, so this breaks it up into the interval from -infinity to -2, union -2 to infinity. And then we test a point in each interval to determine whether the original function is increasing or decreasing on each interval. So we plug in a point into the derivative function. Our derivative is all the way up here, to find out whether the derivative is positive or negative. So I'll plug in, for this first interval, I'll plug in -3. F prime of -3 is going to be 1 over 3 times the cubed root, if you write it like this, 3 times the cubed root of -3 minus 2 squared. Well, this is 1 over 3 times the cube root of -5 squared, and a negative number squared is going to be positive. Okay, so again, I don't really care what this is equal to, I just care that it happens to be positive. And similarly, if I pick some number that's in the second interval between -2 and infinity, like if I plugged in something like +3, I'll get 1 over 3 times the cubed root of +3 minus 2 squared. This is still going to be something positive at the bottom. This entire thing is positive. Now remember what that tells us about our original function f. It tells us that f of x is increasing on the first interval and still increasing on the second interval. Right? It's increasing everywhere. F is increasing everywhere. It's increasing on all real numbers. And so f has no local maxes or mins. So what does that really mean? Well, it means that this critical point at -2 is going to be one of those types of critical points that don't look like a max or a min. It's a critical point where your derivative has a vertical tangent line, or I guess I should say where your function has a vertical tangent line. So maybe it looks something like this, right? Where the tangent line of this function would be a vertical tangent line, but your critical point is neither a max nor a min.